All right, everybody. Sorry about that. We got cut off because I didn't have much data on my phone. But so what I what I did was I hurried up and finished the problem so that we could get through it quick, so that doesn't happen again. Anyway, where we left off was we were going to describe the experimental procedure meant to do that to test the hypothesis that that we were just talking about. We want to provide enough detail, including steps necessary to reduce the experimental uncertainty. Okay, whenever they tell you that, that should be an indication that you should do multiple trials and take an average. That's just good experimental procedures. And then we're going to include a simple diagram. I choose to do that because it really helps clarify things, and the reader then can visualize it much better. And you want to make your responses easy for the grader to award you points. So what I did was I drew this setup. Here's my spring. Here's the sphere inside. And I just labeled the things that I was going to measure. And that's also what you're going to want to do. Okay, so I've got the vertical displacement, the horizontal displacement, and the compression distance. And so then you want to also give some really simple instructions. So the first thing I told them was to set the pin at the position and measure the compression distance with the ruler. Then I said, measure the vertical displacement with the meter stick. And so since they have D and delta Y on the on the drawing, they don't have to guess about what I mean. Launch the sphere and measure the horizontal displacement with the meter stick. Okay, again, very clear. They can see exactly what I'm talking about. And that horizontal displacement I've shown is where that point of impact is. I told them to repeat 3 times at the same setting. So that's where I'm going to reduce my experimental error. And then I told them that I want them to repeat all those steps for settings A and B. Okay, so I've taken care of all 3 settings, and I am repeating each of those. This is not the place to tell them about data analysis. When they ask you about the experimental procedures, just talk about what you're going to do. And then in part C, it says describe how that data could be analyzed to confirm or disconfirm the hypothesis. This is where you're going to talk about what you're going to do with that data. Okay, so just be careful with that, because you don't want to end up repeating yourself. So what I did was I said, well, the first thing we need to do is find the launch speed V. Okay, to do that, what I'm going to do is find the time. And since I've already labeled all these things, it's easy for the grader to see that, hey, I'm using that vertical displacement measurement to figure out my time. And this is just a shortened version, by the way, of your kinematics formula that is on your formula sheet, which goes like this. Okay, now why and why not, that is, I'm sorry, I just replaced y's for the x's that are on the formula sheet, right? When I subtract x naught from x, I get delta x. In this case, delta y, because I'm talking about the vertical direction. There is no initial velocity in the y direction, and the acceleration in the y direction is g. And then I'm just solving for t. Okay, then I'll actually go ahead and calculate the speed for each setting, A, B, and C, using the average displacement for the 3 trials per setting. Okay, again, that's part of reducing the experimental error. And this is my relationship. This is how I'm going to calculate the launch speed. And then we're going to just go ahead and use that to calculate the K using the relationship that we developed back in part A. So normally on these tests, there's going to be some follow through and some linkage between the different parts. So they didn't have you develop this for no reason. They had you develop it so that you could go back and it'll kind of point you in the direction of the data that you need to collect or calculate. Okay, so what I said is that I'm going to calculate this for each of those 3 trials. And if I get a value of K that's very close, maybe I should have said, within experimental error or something like that, then I could say that the hypothesis is confirmed. Now, I'm not going to limit it to just being exactly equal to, because this is an experiment in real life. We're using averages. So, from within a couple percentage for each of the trials, then I'm going to go ahead and say that I've confirmed my hypothesis. Finally, part D. We've got another student using the launcher to consecutively launch several spheres that have the same diameter and different masses. Okay, and each sphere is launched from the same position, launch position, that is, or pin position. And we want to now see how the sphere's mass and the sphere's launch speed, how they vary with each other. And so what I'm going to do is I'm going to say, well, the initial energy in the spring will equal the kinetic energy of the launched sphere, right at the launch location. Now the thing is, since we're going to the same position each time, this doesn't change. My initial elastic potential energy is always going to remain the same. And so then I can go ahead and say, well, the kinetic energy is 1/2 mv squared. If I solve this for v squared, or just get v on one side and m on the other, because I'm looking for a relationship between mass and speed, I'll divide by m and I'll multiply by 2, and I'll get this relationship down here. Okay, so I can see that v, the launch speed, is going to vary with the inverse of the square root of the mass. So this is or I could just say that v squared varies directly with m. So I've got launch speed here and mass here. Well, what happens when the mass goes up? Well, when this goes up, this goes down. And so an inverse relationship would look like this. An inverse squared relationship might be a little closer to the origin in the middle here. Inverse square root might be a little further away, but it's still going to vary like this, where I've got an asymptote on the x-axis and on the y-axis, and you get this concave up shape. Okay, I hope you guys found that helpful, just to walk through. A couple key points is the KISS principle. All of these experimental design questions are going to be set up so that it's kind of obvious what you should be doing. The experimental procedures should be very simple. Okay, if you're writing more than like 5 bullet points, you're doing something wrong, because again, these are supposed to be simple. You're supposed to be able to do this in 25 minutes. Be very clear about what you're going to measure. So even if they didn't give you this table, when you go ahead and you write up your experiment, make sure you're going to tell them, hey, I'm going to measure that vertical displacement with the meter stick. I'm going to measure with the ruler. If I'm going to time something, I'm going to use a stopwatch. You can use motion detectors and things, but know the limits of your motion detectors. Like a motion detector they have trouble picking up little objects, and they're only going to look at motion that's coming towards them or away from them. You're not going to try to capture motion that's going perpendicular to your motion sensor. When they get more than 5 meters away, they're not really picking up much, and it's got to be a pretty big object to pick up at 5 meters away. So if you're going to use more intricate lab equipment, make sure you know the limitations. Almost all of them you can do with like meter sticks, stopwatches, really, really simple rudimentary equipment. So keep that in mind. Also, if you've taken these measurements and you have to calculate something, show like what you're going to be able to do with those measurements in order to get at what you're supposed to be measuring, right? I was supposed to be measuring the velocity, but neither one of these directly measured the velocity. I had to apply principles of projectile motion to figure that out. Circle answers when it's not clear. What else? But just keep it simple, guys. Make sure you're thorough, but not wasting time. Also, another thing is, if you found out that, hey, I went through this, but I had marked something else down here that I should measure, but I never actually measured it in my procedure, go back and eliminate that thing from your list, because you will lose points for extraneous equipment. All right, everybody. I'm really hoping we can see each other very soon. Hopefully after Easter, but we'll see. Daily, weekdays, make sure you check out the review sessions on AP's YouTube channel. Those are going to be at noon for you guys. And then immediately following, we're going to have a live Zoom session to answer anything you have, any questions you have, physics related or otherwise. All right, everybody, stay safe.